All right, let's get started. As I mentioned, I want to start by going over the quiz for Chapter 11. Use that as our way of reviewing the past two classes. And then we'll dive into some new stuff, which is technically new, but it's just an easy extension of the stuff we've done in the previous two classes with calculus. So let's start with the quiz review. Question 1, kayakers like to paddle Slippery Rock Creek, this place in Pennsylvania where it's safe to paddle between 1 and 4 feet of water. So we're going to let h of t represent yesterday's level in feet, t hours after midnight. So we are given a function. Put this down here. H of t equals, what does it say? Let h of t represent river level, t hours after midnight. River level, t hours after midnight. Okay. Alright, it happened that, okay, and we're given h of 13 equals 3.5. H of 13 equals 3.5. And h prime of 13 equals 3. Okay. 3. Okay. So we want to intuitively understand what h of 13 and h prime of 13 mean. Sanjay, can you take h of 13 for us? Equals 3.5.
I didn't do quiz 11 yet.
Oh, you didn't?
No. I thought you were talking about the other two.
All right, well, that's okay. You gotta give you a jump start. What do you think? Take a crack at it.
H of 13.
Mm-hmm. All right, Nikita, why don't you start us off?
I have already
What's that? Yeah. Yeah.
The age of 13, it says after yesterday midnight, around 13 hours, it could be considered as 1 a.m.
Yes.
So 1 a.m. river level.
Wait, no. It's actually 1 p.m. I noticed that was wrong on your quiz, but I didn't take off for it.
Yes,
because
yes.
it's midnight, so midnight plus 13 hours
yes.
is 1 p.m.
Yes, so it's after 1 p.m. The river level is 3.5 feet due to the flash flood.
Yes. Yes.
Trees.
All right, so we've got a function. We input the time, and it spits out water level, flood level. And it's safe to kayak between 1 and 4 feet. So, Sanjay, we input 13 hours, and it spits out 3.5. All right, now, h prime of 13 equals 3. Let's first ask ourselves, what is h prime? Let's back up a minute. What is the derivative of any function tell us? Speed is specific. Rate of change. All right, the derivative in any function tells us the rate of change. So h is a function that tells us the river level. H prime is going to tell us the rate of change in the river level. So, with that information,
the river level is increasing at the rate of change or speed of 3 feet after 1 p.m. or midnight.
At time 13 hours after midnight. So at 1 p.m., the water level is increasing at the rate of 3 feet per hour. And we know that the rate is always already at 3.5 feet. And it's at 3 feet per hour, so that means it's going to cover 20 minutes, it's going to be a full foot, so 10 minutes it's going to be beyond. All right, should we keep going? Should we give Sanjay all the answers? I guess.
I'll review later on.
I guess, and whoever else wants to watch the video, I'm not sure if, like I said, I want to base most of everyone's grade on the final anyway, because the quizzes have been so crazy. So let's just do it. Let's go forward with my plan. All right. Find the derivative of 8x squared plus 2x minus 12. So 8x squared minus 2x minus 12. All right. So f of x equals this. All right, if I were to ask you to find the first derivative of this function, how would you do it, Sanjay? This is your quiz right now. If you get this right.
All right. First derivative. 16 x minus 2x. Minus 12.
Okay. How'd you do this 16? What did you do for the 16? How'd you get this from 8x squared to 16x?
Oh, I'm sorry. 64. Right? 64.
No.
No, no.
You got it right.
Okay.
You take the 2 times the 8,
Yeah.
and that gives you 16. And then you take the 2 minus 1, gives you x to the first power, which is just x.
Okay. So it's just 16.
Yes. No, it's 16x. That's right.
Okay.
But you just didn't do that same thing over here.
Oh, okay. So that's just x.
Yes. All right. So
Okay.
this becomes x to the 0, which is not becomes x to the 0, which is 1. And this constant goes away. This is the first derivative. Right?
So
That's it. That's the answer. Right? Right?
Yeah, because we told that it is 0.
The first derivative, f prime of x, is this. Okay. What else do we have here? All right. Let's move on from this. Just review the power rule. Yeah, review the power rule, and then you remember the constant rule. Any constant, the derivative of that is 0. Okay. All right. Let's move on then to tonight's lecture. All right, let's take a look at this function. Suppose I were to tell you, I'm going to give you a graph equating advertising with revenue. You tell me how much advertising your company is spending. I'm going to tell you how much revenue your company will generate. So I have advertising on the x-axis, the independent variable. On the y-axis, the dependent variable is revenue. So this red graph equates the two. So tell me what's going on as I spend more and more advertising dollars. I start at 0, and then I start spending more and more. Walk me through the story of what's happening when I spend more and more.
So you started at 0. You started spending some money. Revenue started going up.
Yep.
Then you stopped spending. It kind of went flat for a little bit.
I stopped spending.
While you maintained whatever you were spending.
Okay. Was I spending more on advertising or less?
More.
Yeah, I keep
Yeah.
spending.
And it's,
Okay.
and it was flat.
I keep spending, but what happens?
You didn't. The revenue didn't go up, and then it actually eventually went down.
So it went down. Am I spending more on advertising?
Yeah.
And it's going down.
And it's going down.
Why am I doing that? Am I crazy? I spend more on advertising and I get less revenue. Okay, and then what happens?
So you keep spending more, and then it goes up. And
Okay.
it keeps trending up from that point on. as you keep
What about this
spending
part
more.
right here?
It's a constant.
What happened there?
The constant you're spending money and you're getting the profit at the revenue.
I'm getting the profit what?
Like we are spending more money on revenue but at the same time we're getting the revenue. We're spending more money on advertising, but at the same time we're earning revenue.
I'm earning revenue.
Yes.
Their revenue is constant.
Yeah.
Right here? Right here? I'm
No.
spending more money?
No, right here it stopped.
What happened here?
Nothing is like no revenue. We're spending money, but we're not getting revenue.
Yes, I'm spending money, no return.
Mhm.
All right, and then after that, I spend money and I get a return. Now, look at how I initially started. That's all correct. Thank you, Bob. That's exactly how I want to start this class. So, but look at the nuances, though. As I spend a little bit of advertising, my revenue shoots up. So the difference between here and here is a lot. So if I'm sitting in the boardroom, I'm going to say, we need to really spend that first bunch on advertising, and we're going to make a killing as a result. But then, as this curve starts to flatten, our return on advertising decreases. We get a little bit less for bang for each buck of advertising. And then, as you pointed out, it stops. All right, we're spending money, but our advertising, our return, our increased revenue is zero. And then not only that, we spend more money and our revenue goes down. Whatever, people get to know us as the company that has those annoying Super Bowl ads that they paid $1 million for that are a joke. And then it bottoms out here, all right? Whatever might have happened there, I don't know. We've just reached, we saturated the initial market, but then maybe we expand to other markets. Like we run so many of those annoying Super Bowl ads that we reach another market, and then it goes up again. Similarly here, if I'm sitting in the boardroom, I'm going to say, look, you spend just a little bit more. I know this may not make sense because we've just gone through this period where we spent a lot on those ads that didn't pay off. You're going to make a killing on revenue. And then it levels off, and but then it decreases. So this initial function, f of x, we put in advertising and it spits out revenue. I want to make a note of what happens at each of these points on f of x. F of x is just a regular function. Input advertising spits out revenue. So at this point right here, let's see here. This point here, it is increasing, right? Increasing. From here to here, we put in advertising, we get an increase in revenue. At this point here, where the little dot is, it is flat. Flat. Okay? And then from, let's see, from this point to this point, as I put more advertising, what is happening to revenue? Decrease, exactly. Decrease. All right, at this point here, it is flat. Flat. All right, and then same thing here. All right, from here to here, as I put in more advertising, what happens to revenue? Increasing. Fantastic. Increasing. And then here it is flat for a second. And then from here to infinity is increasing. Okay. So we've got increasing, flat, decreasing, flat, increasing, flat, increasing. Let me write this a little bit bigger. Increasing. Ink. Ink. Now, tell me what is happening at each of these points with the derivative of x. Is it positive? Is it negative? Or is it 0? That's the question we're going to be answering for the next 5 or 10 minutes. And it's only those 3 possibilities. Positive, negative, 0.
Positive.
All right. Positive where?
In the increase.
That's right?
Positive.
Yes. Positive. All right. How about this little
0.
0? Yeah, okay. All right. Way ahead of me here. I guess it's not going to take 5 or 10 minutes. All right. What's happening here?
0.
Sanjay? Negative. Yes. Yes. It's a negative slope. All right. And how about here?
0.
Yes. How about here?
Positive.
Positive. How about here?
0.
Nice. And how about here?
Positive.
Okay. So any point on the graph from here to here, we've got an upwards slope. At this point, we have a flat slope at 0, negative slope, 0, positive, 0, positive. Okay, so this gives us some important information. If we know where the first derivative is 0, we know where potential change points, inflection points. We might find a maximum revenue, we might find a minimum revenue, or we might just find an inflection point, a point that is important to know. Well, it's going to level off here, but if we get past this point, it's going to continue up. Now, if I'm looking for the maximum or minimum revenue, this is a great way to do it. I could find where the function itself has a derivative of 0, and I know that that is the only possible place I could find a maximum or minimum. All right, if I know, like, if I'm looking like right here, I say, well, it's increasing here, it's positive here, I know that's not a change point. I know, so the maximum's not here. I need to look at these inflection points for the keys in terms of where the maximum and where the minimum is. And that's what we're going to do tonight. We're going to think about, here's the function, find the derivative, find the maximum revenue, find the maximum profit, find the minimum number of employees. Those types of questions. That's what we're going to use calculus for tonight. Right. So let's do that by taking a look at a couple of examples. Let's turn to page 688. Let's look at number 1, number 5, just a couple little warm-up things. All right, take a look at number 1. For each function, list the intervals on which the function is increasing, intervals on which it is decreasing, and the location of all local extrema. So local extrema just mean the extreme points on that interval. And the local extrema could be an absolute minimum or absolute maximum depending on the shape of the graph. But so basically, for the first one, just look at it and tell me, where is that function increasing? Where is that function decreasing? And the location of the local extrema. All right, well, I can give you a hint. As you go from left to right, the first part of that graph is decreasing. Hey, Shiva, how you doing? Oh, no problem. And it decreases. When does it stop decreasing? At what point on the x-axis does it stop decreasing? That is correct. X equals 1. So at x equals 1, that stops decreasing. And when does it start decreasing? We haven't really covered this yet, but so I'll just tell you. It starts decreasing at negative infinity. Because you see that arrow on the left-hand side? That goes on up to infinity, and it goes out to infinity. So it starts decreasing at negative infinity, and it stops decreasing at x equals 1. All right? Then where is this graph increasing? Ah, 688. It's 1. It's the same place.
It's the same place.
Yeah, it's x equals 1.
Yeah.
Yes, from x equals 1 until infinity, it is increasing. And where is the local extrema? That would be a minimum or maximum on that interval. 1. X equals 1, and it's x equals 1, and y looks like it's negative 1, 2, 3, 4. So it's x equals 1, y equals negative 4 is a local extrema. Local extrema just means it is a extreme measure on that interval, which we have identified. We've identified in this case it's negative infinity to positive infinity. And also just by looking at this is this an absolute minimum to this function? Is there any point lower than the point at 1, -4? Or is that the lowest point on this function?
It's the lowest point for the graph.
Exactly. It's the lowest point for the graph, and we know that it's the lowest point for the graph because on the left and on the right it goes on and up to infinity. We know it doesn't turn around because it gives us that arrow. Okay, so we just talked about looking at increasing interval, decreasing interval, the local extrema, and then we looked at this graph and said not only is this a local extrema, it is an absolute extrema. Let's try the same thing with number 5. All right, this gets a little more interesting. So, same questions. Tell me, where is this function h of x? Where is it increasing? Where is it decreasing? And where are the local extrema? And then we'll ask if we have absolute extrema at either of those points. All right, Sanjay, you want to walk us through?
So it starts increasing at y equals infinity,
X equals negative infinity.
x equals negative infinity.
See, because X is on the horizontal axis, and to the extreme left is infinity. So it starts increasing at X equals negative infinity. Okay. And when does it stop increasing?
It starts decreasing at x equal -4.
Yeah, that's good enough. We don't need the y. So from negative infinity to -4 on the x-axis, it's increasing. All right. And why don't you take the next step for us, Nikita?
It's again decrease at -2
So it's decreasing from where to where?
from the negative x, -4 to it increases again from -2 it decreases to
Wait, so from -4 to -2, it does what?
decreases
Yep. And then from -2
to
how far does that? All right. So from negative, I know what you can say. From -2 to something else.
to x of 2
-2 till where? Till where?
to as horizontal x of 2.
So from -2 to infinity, it increases. Okay, does that make sense? That off to infinity, it increases?
Yes, it is.
And the reason why I belabor that point is because we know it's increasing off into infinity, then we can look at these little points where the humps are, and we can make assumptions about those. Like if we didn't know it increased to infinity, maybe it decreased and went down, that might mess up our attempts to claim that's an average or that's an absolute minimum, absolute maximum. Okay, so Nikita, just walk me through from the beginning. Start at negative infinity and go to positive infinity on the x-axis. Tell me where this graph is increasing, decreasing.
So from infinity to -4.
Yes.
-4, the graph is increasing,
Yes.
and then from -4 to -2, it is decreasing.
Yes.
Then again from -2 to infinity, it gets increasing.
Perfect. All right. Now tell me the local points of local extrema. There's 2 of them.
What was that again? That was the
Extreme point.
Let me give you a better definition. I just threw that at you. It's the point where. Yeah, I can't read the definition. All right. If f of x has a local extrema, function is said to have a local extrema. It's a point around which it's when the graph changes. C3 and now the function is said to have a local extreme. Let's see if the local means point around which this is local extreme and all numbers. They don't give us a definition per se, but it is. It's on one side the function is increasing, the other side the function is decreasing. There's a, I guess it's a flat where f prime of x equals 0. Let's go with that, Sanjay. Where the first derivative is 0. So the slope is 0. We'll call that a local extrema. No, we can't call that a local extrema because it's a high point or a low point on that interval. That's what it is. All right, I should rewind the tape and edit out that terrible attempt to explain extrema to you, Sanjay. We'll call it an extrema is a high point or a low point on that interval. You like that, Shiva? Extrema is a high point or a low point on that interval. So if I were to ask you what's the local extrema between the high point, what's the high point between x equals -4 and x equals -3? Yeah, -4 is higher. So that's the local extreme. Local extrema is high point or low point on that interval. So there are two, on question 5, there are 2 high points, or there are 2 points that meet that definition. Where they're -4 and -2. So -4 and -2. Now, if that is an absolute extrema, meaning it is the highest point on the function or the lowest point on the function, that is important for us to know. So that's my question now. We've identified 2 local extrema, meaning high point or low point on that interval. Now, tell me, are either of those absolute extrema, meaning the highest point on the function or the lowest point on the function? No, because x is going to negative infinity on the left-hand side, positive infinity on the right-hand side. Those are the absolute extremes. So if I were to give you this function, I might be able to say, or you might be able to say, well, when x equals -4, we know something about the maximum revenue during that time period. When x equals -2, we know something about the minimum revenue during that time period. But it's not the absolute minimum or absolute maximum. Okay, let's try that same thing with number 7. Where is it increasing? Where is it decreasing? Please tell me the local extrema, and then tell me if any of those are absolute extrema. Whoever wants it, walk me through. Start with x equals -infinity. Tell me where that graph is increasing, decreasing, or there's a local extrema. I'm sure you two have it. I don't want to pick on Bashiba because she just sat down.
Is it
You
going
wanna
up negative?
So do you want to start number 7? Start with the
Oh,
x.
Yeah, x-axis looks like it's this way, and move to the left, underneath -4.
Well, so we move to the right. So let's move to the right. Let's start at
To the right?
Yeah, let's start at the left on the left-hand side, and as we move to the right, what's happening to that graph?
It's going up.
Yeah.
No.
As we move to the left,
Move to the left.
excuse me, move to the right.
To the right.
Look, take a look up here, Shiva. Suppose I were to tell you, as I move from the left to the right, and increase advertising spending. So I'm moving this way. What's happening to this graph? All right, tell me as I move. What's it doing now?
Staying the same. It's
It's going up. It's increasing. So as I spend more on advertising, the revenue increases. So as I go to the right, it is
staying the same.
the revenue. The graph is increasing.
Yeah.
Yeah. So as I move to the right, what's happening over this interval with the function?
It's like on the Y.
Yeah, the y, the revenue. So as I spend more money on advertising, what happens to revenue?
Goes up.
It increases.
Right.
Yeah. Okay, so as I move to the right on the graph, what happens to revenue? What happens to the function? Yes. All right, and then I get to this point, what happens is I spend more on advertising. Yeah, it flattens out to 0, and then it starts to decrease. All right, and it decreases until I get to here, it flattens out to 0, and then as I keep spending more advertising, it increases. Flattens out to 0, more advertising increases. Okay. So, all right, so who's going to do number 7 for us? I don't want to spend all night on number 7. Yeah, okay, thanks.
So x equals negative infinity.
Okay.
Starts to decrease. Right?
Yes.
Decrease to negative 7.
Yeah, looks about right. 4, 5, 6, 7. That's right.
Negative 7. Then it increases to y equals 3. So it peaks.
It decreases till x equals negative 4. But y does equal 3. That's right. Okay.
Oh, so it's just the x, okay. Then it decreases to x equals negative 2 to, and then starts to increase to x equals negative 2 to infinity.
Yes. Yes. All right. So if this were advertising on the x-axis, you would, advertising on the x-axis, you would say we've got decreasing revenue based on advertising, we've got increasing revenue, then a period of decreasing revenue, then a period of increasing revenue as we spend more and more on advertising out to infinity. So next question. Please tell me where the local extrema are. Local extrema means high point or low point on a certain interval.
X equals negative 4.
Yes. That is one. I see 2 others.
X equals negative 7 and negative 2.
Yes. Okay, so we have 3 local extrema. So the important thing about local extrema is there are possible points for absolute extrema. So next question. Are any of those 3 local extremas absolute extremes?
X equals negative 4.
That's, what is that? The absolute high point, absolute low point?
Absolute high point.
Absolute high point. All right, what do you think, Nikita? Sanjay says x equals negative 4 is an absolute high point.
Oh, no, because you have to infinity. Like that.
Negative 2.
Okay, negative 2, what about negative 2? That is an absolute what? Extrema?
Extreme.
Yeah, and it's a minimum.
Yeah.
And it's tied, I guess, with x equals negative 7. So those two share the title of absolute minimum on this graph. Is that making sense, Shiva? All right, so we're just thinking as we move from left to right on the graph, what's happening with the y-axis? Is it increasing or is it decreasing? And then we look at points, these inflection points, where there's a potential, where there is a local extreme, a potential local extreme. And that potential local extrema could be an absolute local extrema. And looking back to our example, where we looked at this function, advertising and revenue, the points where the first derivative is 0 are points of local extrema, potentially, on this graph. And this one is a little bit tricky because there's one that we haven't really dealt with yet. At this first point, where the derivative is 0 and the first derivative is 0 and the function levels off, we're going to call that a local maximum because there's a point lower than it to the left of it, a point lower than it to the right of it. This point also is a local minimum. All right, it's higher to the left, higher to the right. This point, there is a point where the slope equals 0, but this is not a local extrema because it's lower to the left and higher to the right. All right, this point is higher than this. So on anywhere around this interval, we're going to have higher values to the right. And similarly, if we were to ask the same question we asked in the previous ones, is this an absolute maximum or an absolute minimum? Well, they're not. This is not the absolute maximum because we know this part is higher. This is not the absolute minimum because we know 0, where it started, is lower. All right, so this is going to make sense as we start to, I'm sure it's making sense already, but you may be wondering why I'm belaboring what looks like a simple point. So let's look at a couple examples. All right, how we would put this into practice. So how we're going to approach this is we are going to be given a function, and if we want to find, all right, what maximizes or minimizes the values on that function, we're going to do two things. One, we're going to take the derivative of that function, and two, we're going to find out where that derivative equals 0. And then we're going to do a third thing, actually. We're going to look in between those points, and we're going to see, is the first derivative, is it increasing or is it decreasing? And what does that tell us about whether or not this is a local extrema, and is it an absolute extrema? And these numbers here, I guess I didn't cover this, these points here, where the first derivative equals 0, we're going to call critical numbers. Critical numbers. All right. So our first step is to find these critical numbers. Our second step is to determine whether or not they are local extrema. Our third step is to figure out whether they're absolute extrema. So let's do that with an example. All right, if I were to give you the function f of x equals 2x to the third x to the third minus 3x squared minus 72x plus 15. All right, if I were to give you this function and I were to say, I need to know the maximum and minimum values along that function. This might be a revenue function. I tell you I want to find the maximum revenue or the minimum revenue along that function. You're going to do those three things. You're going to find the critical numbers. Well, first you're going to find the derivative, and then you're going to find the critical numbers. And then you're going to determine if any of those are local extrema, and then if any of those are absolute extrema. So the first step is we find the first derivative, because we want to know where the first derivative equals 0. You with me so far? So let's find the first derivative of this function. So f prime of x equals, all right, what do we do with this? 2x to the third? Yeah, how do I get the derivative of this?
3 to 6, 6x squared.
6x squared, fantastic.
6x
Minus 6x, minus 72, and this goes away. Okay, fantastic. Now, this is the derivative. Second question is, where is this derivative equal to 0? What can I put in for x that would make y 0? Because this is telling us the rate of change, the derivative. So this is, when I put in a certain x, if the slope, it spits out as 0, I know that that's an inflection point that could be a local extrema and could be an absolute extrema. So I set this equal to 0. 0 equals 6x squared minus 6x minus 72, and I solve for x. Is this looking familiar? Is this something you've done before? Solving for x? All right, so let's think about how we might do this. All right, first thing we can do, I see 2 6's, and I know 72, I can divide 6 into 72. So I may be able to do something to get rid of those 6's. So let me take the 6 out, which leave me with x squared minus x minus, if I take 6 out of 72, that is, what's 72 divided? 12. Yes. Minus 12. Okay, equals 0. And then who knows what I can do with this 6 now that I've got it pulled out? I can divide both sides by 6. Alright, so I can divide this by 6, and I can divide this by 6. So what do I get when I get 0 divided by 6? 0. So it's just a great way of getting rid of the 6. So this divided by this is 0, 6 divided by 6, this cancels, this cancels, this cancels. So now I'm down to 0 equals x squared minus x minus 12. Does anyone know what we might do at this point?
12x cubed.
12x cubed? Well, alright, let me throw this out and see if this looks familiar from past math courses. Suppose I want to try to factor this somehow. Yeah, do one of those deals. It's not going to be quite like that, but it's going to be something like that. What could I multiply together to equal this? And if I have two things that I could multiply together, I know that each one of them could be 0. So this times this, either one of those could be 0 to make this true. I think I'll repeat that when I flesh this out. But let's think about how I could split this x squared up. All right, maybe I could do two things I'm going to multiply by each other. And I could put an x here and an x here. Because if I multiply these times each other, this times this would be x squared. All right, so I'm potentially on something that is legitimate. This number, I guess, end part of the bracket, I know ultimately I'm going to need to multiply this part by this part to get negative 12. So there's a number of possibilities. I could put 1 here, I could put 12 here, I could put 2 here, I could put 6 here, I could put them the other way around. They could be negative and they could be positive. And this is just a trial and error process. But the important information is I see this middle number is negative x. So I know when I sum the things that I'm going to multiply in this together, there's going to be a point where I need one more negative x than I need positive x's. So let's just try 3 and 4. Okay, let's see, what if I put trial and error, because I think those are going to add up to one being more negative by 1x than the other, and that's going to give me what I need. So let's just see if that works. If I put a negative 4 here and a positive 4 here. So I've gone through a process where I've thought about how I would factor that. And my question now is, are those two things equal? Is this figure the same as this figure? And if it is, then we're good. So let's decide if it is. So how would I multiply these things out if I were to? Let me open up the brackets here. So let's just do a little side note. X plus 3 times x minus 4. Okay, so I would start by taking x times x and then x times negative 4. That's how I would factor that out. So x times x is x squared. X times negative 4 is negative 4x. Right? Alright, so now I have taken this first x and I've multiplied it by both things in the other bracket. Second thing I need to do is I need to take the second number and multiply it by both things in the other bracket. So I take the 3 times x, gives me positive 3x, and then I take the positive 3 times negative 4, gives me negative 12. Right? Can I combine these two middle terms? So that leaves me with x squared minus x minus 12. Is that the same thing? That's x squared minus x minus 12. So what I can conclude is this is the same as this. Does that make sense, Shiva? You're not going to lie to me. I can tell. Sanjay, is this making sense? This look vaguely familiar from algebra?
From the other day.
We can spend a little bit of time on this example. There's not a whole lot of new content besides this critical number stuff. Just don't want to lose anyone at this point. So let's think about why these two are the same again. It's just a product of how I would do the algebra. Just a function of how I would do the algebra. If I were to, let's think of an example. If I were to say, let's see, 1 plus 6 times 2 plus 3. Okay, how would I factor those out? Well, I could just add 1 plus 6, which would give me 7, and 2 plus 3 would be 5. So 7 times 5 is 35, right? Alright, but let's make it more complicated. Let's go 1 times 2 plus 1 times 3. Alright, so 1 times 2 is 2. 1 times 3 is 3. Plus 3. Okay, that's the 1 plus both terms in the second bracket, parentheses. Now let's do the 6 times 2 plus the 6 times 3. So the 6 times 2 is 12, so plus 12. And then the 6 times 3 is the 18, plus 18. So I hope that adds up to 35, doesn't it? Yes, all right. Nikita says it adds up to 35. All right, so that's the algebra of what we did. We just said, all right, how can we make something that's in parentheses equal to something that is fleshed out. How can we make this thing in parentheses equal to the fleshed out version? And we did it. We did it without violating any rules. And now we're at this point. We're at x plus 3 times x minus 4 equals 0. So here's what's interesting. If either of these two things are 0, then that makes the answer 0. So if this was 470 and this was 0, would this equation be true? So this would be 0 equals 0 times 470. Is that true? Yeah.
Yes.
0 times 470 is 0, so 0 equals 0. That's fine. All right, how about if this were 7 billion? All right, and this number were 0. So 0 equals 7 billion times 0. Is that true?
Mm-hmm.
So if either one of those is 0, that makes this equation true. So what this tells us is there are 2 points on this graph that are 0. It either could be 0 equals x plus 3, or 0 equals x minus 4. 2 possibilities for 0. All right, so if so what would x equal in this case?
3.
Close. 3 plus 3 equals 0? No.
Oh.
I know you get it. I know you have it. What do I have to put in for x to make this equal 0?
0.
0 plus 3 equals 0? No. What do I have to put in for x to make this equal to 0?
Minus 3.
Bingo. Minus 3. So minus 3 plus 3 equals 0. All right, what do I have to put in for x here to make this equal to 0?
Positive 4.
Positive 4. 4. Okay, so I know there are 2 points where the derivative is equal to 0. X equals negative 3 and x equals 4. So those are those 2 points along my graph where I've got a slope of 0. And I know those are possible local extrema. And I further know that those are possible absolute extrema. Alright, so I was given an original function. My instructions were to find possible local extrema and find possible absolute extrema. So I took the derivative of that function. I set the derivative equal to 0. Because where the derivative equals 0, that means that's one of these points. That's one of the critical numbers. I found the critical numbers at negative 3 and 4. The next thing I need to do is determine what's happening on either side of those critical numbers. So let's do it. Let's think about the interval here. Can I erase this part, this half part here? Better not. All right, I'll leave it up for a minute. Let me take just a timeline here. Not a timeline, just a line on this for this function. All right. Okay, so suppose I'm interested in certain numbers. Can you all see this? Maybe you can. Can you see it? You see it? I'm interested in certain numbers. Say this is the x-axis. I'm only interested in the x-axis at this point. All right, I'm looking at negative 3, and I'm looking at 4. I know these points are inflection points. All right, inflection. F prime of x equals 0. F prime of x equals 0. I want to know what's happening on either side of those points. This is a region that's important to me. And if I take the derivative in this section, and if I see it's increasing, decreasing, I know it's not zero. I know the derivative is either increasing, the slope is either positive or negative, so it's either increasing or decreasing. So what I want to do for these 3 points is I want to find whether or not the function is increasing or decreasing. Let me take a breath right there. So I've got the critical points where I know the slope is 0. The first derivative is where the slope is flat. First derivative is 0. So I want to find out, is this function increasing or decreasing on those intervals? How I do that is I see what's happening with the derivative at any point to the left of -3. It could be negative infinity, I could plug it in. But let's find something that's easy. All right, let's test -10. All right, let's test that point. See whether or not we can determine if the the function is increasing or decreasing. In between -3 and 4, let's pick an easy number. Let's test 0. All right, and above 4, let's see if we can find another number. Let's test 10. And I want to find out what's happening with the derivative at that point. Let's start with -10. So I know the derivative, this is the derivative function. This tells me the rate of change for the original function. So if I plug 10 into this function, it's going to tell me the slope at point 10 for this function. Does that make sense? So let's do it. Let's plug 10 into this function and find out what the slope is. 10 squared is 100, times 6 is 600, excuse me. So 600 minus 10, 6 times 10 minus 60, minus 72. Is this what's 600 minus 60 minus 72? It's like 400 something?
minus
600 minus 60 minus 72.
468.
468. Okay, so that's a large number, whatever. Is it positive or is it negative?
Positive.
It's positive. So what does that tell you about the slope at point 10 on the function?
It's increasing.
It's positive and the function is increasing. Okay, so I know, all right, 10. Yeah, so 10. So point 10, so this is the point we tested here, 10. All right, I know at this point, the function is increasing. Because I know that at point 10, we have a positive slope, and I know that there's no further inflection points as we go out to infinity. All right, let's test 0. Let's put 0 into this function. What do I get? F prime of 0. What's that? No. This is where I set it equal to 0 and find the critical numbers. Now I want to find what is the slope of this function at point 0. So I put 0 into this first derivative function. And what do I get when I put 0 into f for x here? Close. Actually, not that close. Negative 72, exactly. All right, I put f prime of 0 as negative 72. All right, so the slope at point 0 is negative 72. So the actual function, is it increasing or decreasing? It's decreasing. Yes. So from this interval, at this interval, from -3 to 4, we know this function is decreasing. We know also there's a possible change in direction, though, at -3. So let's find out what's happening over here. Let's put -10 into the first derivative. And let's do f prime. Let's do f prime of -10 equals. How much?
588.
588. Okay, good. Is it positive or is it negative?
Positive.
Positive. So what's happening to the initial function at x equals -10? Increasing. Okay. All right. So take a look at this little graph. I know from -infinity until -3, this function is increasing because I took the first derivative. All right? And then I know there's some inflection point after which, from -3 to 4, the function is decreasing because the slope is negative. And I know it keeps decreasing until x equals 4. And then what happens after x equals 4? It increases. Okay. So I have identified 2 local extrema. This is one local extrema, and this is another local extrema. This is a local maximum along this interval. This is a local minimum along this interval. Next question. Are these local minimum and maximum? Are they absolute minimums or absolute maximums?
Absolute minimum.
This one's an absolute minimum? What about this one?
No.
No?
At the end, it's again increasing.
Because at the end it increases and goes up to infinity. And it gets to infinity. It doesn't matter how steep it is. It'll get to infinity eventually. All right, so this is not an absolute maximum. Is this an absolute minimum, though?
All of that goes to infinity.
This goes to infinity negative. Okay, so these are just local extrema. They are not absolute extrema. Does this make sense? Sort of? All right. It's going to sink in. So I might ask you a question. All right, what is the maximum profit over this time period? And you might say, well, this is the maximum profit, this is the minimum profit over this time period. If I were to say, what's the maximum profit ever, then you wouldn't be able to make that same type of assumption. All right, so let's back up and see what we did, because this is all we need. This is all we're doing tonight. It's this, and now we're going to apply it with a few examples, which are going to be complicated because this is fairly complicated. But let's just walk through. What do we do? I started off by giving you a function. Maybe it was a revenue function. Maybe it was a cost function. You didn't know exactly what it was, but I said this is a function f of x. And I asked you, please find the local extrema on this function and tell me whether or not they are absolute extrema. That's what you were tasked with. And it may have been because I wanted you to find maximum revenue, maximum profit, minimum cost, variety of questions I could have asked you. But I said, please find the local extrema and tell me whether or not they are maximum, absolute extrema. How did you do that? Well, first you took the first derivative of that function to determine where the slope equals 0. All right, if this were the function, it would be these points. You're going to find where are these points. These are the points I'm looking for. That's the first thing I need. I need to find where the slope equals 0. So in order to do that, I need to take the derivative of this function and set the derivative equal to 0. And you did it, and you did that. This is the derivative, and then you set this equal to 0. Then you used some algebra. First thing you did is you took this 6 out, You divided both sides by 6, and you got an equation that was a little easier to manage. This x squared minus x minus 12. And then you factored it in a way that you thought of years ago in high school, but haven't really thought about since. And you said, well, if I factor it, I can isolate two numbers that would make this equation true. And they are -3 and 4. I have found my critical numbers. Critical numbers could be local extrema. Local extrema could be absolute extrema. Now I know those are the only two places where the first derivative equals 0. And this is important in these assumptions. I know as we go further and further out in x, I know this does not change direction. Because there's no other point beyond 4 where the slope equals 0. There's no other point where the first derivative set to 0 equals 0. 4 is the end of the line. And -3 is the beginning of the line. So all I need to do is find out what is happening to that function to the left of -3, between -3 and 4, and past 4. So I put in two test numbers, or 3, excuse me. Any point. I just tried to make the math simple, so I chose 10s and 0s. And then I put this number into the first derivative. I didn't put it into the original function. I put it into the first derivative. And if the first derivative is positive at that point, that means it's increasing. All right? Remember, positive. Remember, this is increasing, this is positive. Decreasing, negative. Increasing, positive. Increasing, positive. If that first derivative was negative, I would know that it was decreasing. All right. Very last piece. Suppose, now that I know this is a local maximum and a local minimum, I want to know the value of the function at x equals -3 and x equals 4. All right, how much, if this means advertising, how much revenue do I get at x equals -3 and x equals 4?
You have to put 10 to the derivative -3.
Yeah, and I would put it back into the original function. If I put it in the derivative function, it just tells me the slope. I put it into the original function, it tells me a value, whatever the value is. Don't let that last part confuse you. It'll make more sense when we have a concrete example where we can do it. But as long as you're feeling good about how we got to here, then I'm feeling good about moving on. You like this? Move on? All right. Let's see, 685. So in this, what I did, just for your information, what I did is I used example 4 and example 5 on page 683 and page 685. That's the problem you all just worked out. And did you see that, Shiva? You might want to just circle that so you can. Yep, example 4 and example 5. So that's exactly what we just worked out on the board. So when you're trying to fall asleep tonight and you're like, how did that work? How did that go? Just pull out your book, turn to page 683, look at example 4, look at example 5, and we can work it out like that. Okay, let's see, 686. All right, sales. Okay. Example. Cut. Okay, so let's turn to page 713, and let's do number 25. 713, number 25. Start taking a look at that while I make some room on the board for us. cartoon number 25. So the daily cost of producing X high-performance wheels for racing bicycles is given by the certain function. C of x equals 0.01x cubed minus 1.5x squared plus 175x. And no more than 100 wheels can be produced each day. What production level will give the lowest average cost per wheel? What is the average cost? Okay, so this function, it's a function of x. So if we put in x, what does this function spit out, so to speak?
Rate of change.
We're not to the derivative yet. So the daily cost of purchasing X high performance wheels. So I want to know two things. What is the X that we're inputting, and what is the Y or the answer that it would spit out? Don't think about the derivative yet. Go ahead, Sanjay.
Number of high performance wheels.
Exactly. All right, so however many high performance wheels for racing bicycles we want to produce, that's what we input for X. Say we want, and the maximum we can produce is 100. So say we want to produce 70 a day. We put in 70 for X, and what will it spit out?
17.
Yeah, say we put in 70 for X, and it will spit out what, Sanjay?
The cost to produce the
Exactly, the daily cost. So we put in 70, so we put 70 cubed times 0.01 minus 1.5 x squared plus 175 times 7. You don't have to crank it out, but just as long as you all understand the intuition there. So if I wanted to produce 90 bicycles a day, how would I find my daily cost?
6.90.
Exactly. All right. Suppose I want to produce 20 bicycles per day. Shiva, how would I find the daily cost of producing 20 bicycles per day? Yeah. Yeah. And 20. Just talk me through some of the math. What's the first thing I would do? X. If I put in 20, I would do 20 cubed times 0.01. And what would I do next? Minus 1.5 times 20 squared. And what would I do last? Plus 175 times 20. I would just put in 20 for X. And I would get on my calculator and I would crank it out. Okay, so same question. What if I wanted to produce 95 bicycles per day? How would I find my daily cost of producing that, Shiva? Yeah, talk me through it.
95 cube
Yes. Times what?
times 0.01.
Exactly. You got it. All right. So I just don't want to get confused on that before we even start. So I put in the number of bicycles I want to produce, and it's going to tell me the daily cost. And this question asks me to find the lowest average cost. So this is a little tricky because there's a step we need to take before we even get started. We need a function for the average cost per wheel. This function gives us the total cost of producing all the bicycles. I need a function for the average cost. Do you remember I showed you, I think either last class or the class before, what's the average cost function?
Something divided by x.
Yeah, something divided by x. So the average cost function for this would be, so average cost at average cost equals C of x divided by x. Alright, the total C of x gives us the total daily cost. It doesn't say average, right? It's just the daily cost divided by the number of bicycles I produce. So I asked Bathsheba a minute ago, I said, suppose I want to produce 95 bicycles. Tell me the daily cost. And she said, well, okay, you take 95 cubed times 0.01 minus 1.5 times 95 squared, all right, which would be the C of x, and then you would divide that by 95. So average cost, say for example, e.g., would be C of 95 divided by 95. The C of 95 is going to give me total cost. Divide that by 95 is going to give me average cost. You like that? Okay. So let's have a function which tells us average cost. And all we need to do for that is we need to take the regular function divided by x. So C of x equals, what is it, 0.01 x cubed minus 1.5 x squared plus 175 x. Okay, so that's our cost function. Now I want to find the average cost. So, average cost equals this divided by, equals C of x divided by x. So I need this whole thing divided by x. 0.01 x cubed minus 1.5 x squared plus 175 x. Divide that whole thing by x. Right? Alright, what do we do from here? I'm going to call this A of x, like av of x. Alright, what's the first thing I do, Sanjay? Can I cancel some stuff?
You can cancel the x's.
Cancel all the x's, right? This one works out conveniently. If it didn't, then we might have some hard work to do. 0.01 x, this becomes squared, minus 1.5 x, just becomes x regular, plus 175, this x cancels that x. All right, so I've got an average cost function. So now, Shiva, I want to know the average cost per bicycle of producing 95 bicycles. How do I find that? I'll give you a hint. I either put 95 into this or 95 into this. Just say top or bottom? Bottom. Okay, this is going to give us our daily cost. Average cost is going to be determined with this function. So if I say I want the average cost of 20 bicycles, which function do I use, Nikita? Average cost, all right? Say I want total daily cost of 99 bicycles, which one do I use, Sanjay?
Second?
I'm sorry. If I want the total daily cost of 96 bicycles, which function do I use? Yep, total daily cost, average cost, boom. Now, I want to find the lowest average daily cost. Those are my instructions. Please find the lowest average cost per wheel. So I want local extrema and absolute extrema for one of these functions. And the question asks for the average cost. Alright, so this is the function I'm going to be working with. This is the function I want to find the lowest point. That's it. I want to find the lowest point. I do have this limitation that I can't produce fewer than 0 bicycles. And I also know I can't produce more than 100 bicycles. So I'm looking at the interval from 0 to 100. I want to find where this is the lowest. right, so how are we going to find where this is the lowest? We're going to do the big example we went through at the start of class, where we said, let's find the first derivative of this. Let's find where the first derivative equals 0. Those are the critical numbers. And once I have critical numbers, I know that those could be local extrema. And once I have local extrema, I know those could be absolute extrema. And if I find absolute minimum, then I know I've found the lowest average cost. Right? And I know whatever number that turns out to be, I plug back into the original function, and it will give me the daily cost of producing that many. So let's do it. What do you say? What's our first step? Find the derivative of this function. All right, so we want AV prime of x equals this 2 times, what's 2 times 0.01? 0.02? Is that right? 0.02x minus 1.5. And this 175 goes away. Right? What's our next step? Yeah! Good job, Shiva.
I wrote that down.
Yes! You're on it. Alright, so I set this equal to 0 equals 0.02x minus 1.5. And this is an easy one. I don't have to do much factoring. At this point, I can add 1.5 to both sides. I can add 1.5 to this side. And I get 1.5 equals, get myself running out of room. I don't want to run out of room here. All right, so 0 equals 0.02x minus 1.5 plus 1.5 plus 1.5. 1.5 equals 0.02x. What do I do next? Divide both sides by 0.02. Divide by 0.02. All right, what do I get? 1.5 divided by 0.02?
75.
75, yes, equals, this cancels, x. This is looking pretty good, right? I've got a nice whole number, and I only have one of them. So there's only one critical number. There's only one possible local extrema, and only one possible absolute extrema. Next, let's do the number line thinger. Alright, now this is going to be easy compared to the last one. My only point of concern, this is x equals 75. An odyssey with markers here. Sometimes they work, sometimes they don't. Craziness. Alright, I guess I'm going red. Going red. Alright, x equals 75. I know that's an inflection point, and it could be a local extrema. So I just need to test one point on either side of it. And I need to find out what the derivative, what the slope is here. And if the slope is positive, that means it's going up. If the slope is negative, it means it's going down. Now what's the derivative here? Positive means it's going up, negative means it's going down. All right, so let's pick some easy numbers. What do you say? Let's pick 0, and let's pick 100. All right, what is the derivative when x equals, what is the slope when x equals 0? That's a question I need to answer. All right, what's the slope here? So I don't put this into the initial function because I want to know what the slope is. So I put this into the first derivative. This tells me at any x what the slope is. So let's put it into this function right here. All right, let's do a v prime of 0. 0 equals,
0.
Sanjay, help us out. Put in 0 for this.
1.5.
Close. Very close. 1.5, you're on the right track, but you're not quite there. Negative 1.5. You put in 0 here.
Oh, yes.
0 times that is 0. Minus 1.5 is negative 1.5. Negative 1.5. Okay. So I know at this point the first derivative is negative. So that means the slope is negative. That means the function itself is increasing or decreasing. Yeah.
Decreasing.
Yep. Decreasing. Fantastic. All right, let's put in 100. See what we get. AV prime of 100 equals negative 50. Okay. Really? 100 times 0.02. Yeah, no.
No.
98.5? Really? Maybe? 0.02 times 100 is 2. Minus 1.5 is 0.5. Okay. 0.5, is that positive or negative? Okay, so the slope at average cost of 100 is positive. So does that mean the function itself is increasing or decreasing? Yeah. All right. So these arrows, this is the actual function, this average cost function. All right. We know that from negative infinity up until 75, it is decreasing. We know at 75, it is flat. There's an inflection point. We know that 75 to positive infinity, it is increasing. So we know that this is a local extrema, for sure. Is it also an absolute extrema? Yeah, why is it an absolute extrema?
That is the most decreasing and that is the most increasing.
Yeah, so from here on out, it's getting higher and higher. From here on out, it's getting higher and higher this way. So this is the lowest point in the history of this function ever. We know that 75 is the point where the average cost is the absolute lowest. We have found the number of bicycles we need to produce for the lowest average cost. And let's see, let's plug 75 back into something and find out what is the minimum average cost. Okay, so what is the minimum average cost? If we produce 75 bicycles, what is the average cost going to be? And I don't want to confuse anyone, so I'll just tell you this was our quote-unquote original function. I know that this one up here was our really original function, but the one we started working with was the average cost function. Before we did any derivatives with it, we created this average cost function. So if we want to find the average cost at 75 bicycles, we put in 75 here. If we wanted to find the total daily cost, we could put in 75 here. That would be fine. The question is, what's our average daily cost? Put in 75 here, and let's crank it out. Average 75 equals 75 squared times 0.01 minus 1.5 times 75 plus 175. What is the minimum average cost? Yeah. All right, so put 75 in there and tell me what you come up with. And Keep your fingers crossed, Sheba.
180.
Yes. 118.75. 118.75. $118.75 is the average cost if we produce 75 bicycles. And we also know that if we produce 75 bicycles, that is the lowest average cost. Because based on the production machinery, all that stuff, supply chains, we've created this equation to tell us how much our average cost will be at any point. What do you think? Good? Good stuff? Do another one? And take a break? I only have two more. Actually, those are just two. I think you only have 3 homework problems, 3 of any length. And that's all I potentially was going to do in class today. So the maximum we have to do is 2 more just like this. And we should definitely do 1. And maybe the third one we'll call optional. Should we take a break now, or just want to do the next one? Do it?
Yeah.
Let's do it. All right, 713, number 27. Take a look at that. And
What number?
27. Just 2 down, I guess. Okay. Alrighty. Oh, this is a good one. I remember this. The number of employees of Amazon Inc. can be approximated with this function. F of x equals 627x squared minus 3530x plus 11,500. X is relevant between 0 and 11. So, and x equals 0 corresponds to the year 2000. What is the maximum number of people employed by Amazon during this period? What is the minimum? Okay. So we've got this function that tells us the number of employees at Amazon. It is relevant starting at x equals 0, which is year 2000. And it continues in relevance till x equals 11, which is 2011. And we want to know the maximum number of people employed by Amazon during this period. We also want to know the minimum. Okay. How are we going to... let me write this equation on the board because I have a strong feeling we're going to be using it. And while I do that, why don't you all think of how we're going to solve this problem? Okay. So this tells us how many employees we have at Amazon. So x equals the year, and x equals what is it? How do we write it? X equals 0. X equals 0 is 20,000. X equals 0 is the year 2000, and x equals 11 is 2011. And wants to tell me the maximum and minimum. So if I were to ask you, how many employees were at Amazon in 2003? How would you solve that? I'll give you a hint. This is an easy question. No.
First we have to find the function, like 627 multiplied by 2 and whatever.
Derivative, you want to find the derivative?
Mhm.
Okay, no. It's not that complicated yet. The only question I'm asking now is how many employees were at Amazon in 2003? And the answer to that question is you just put in 3 for X. And it spits out the number of employees. So how many employees were at Amazon in 2009?
With 9 units.
Yep. All right, Sheba, tell me, how would I find how many employees were at Amazon in 2007? I would use this function. I would put something into this function.
The function is 627?
Yep. It is a tiny bit confusing because X equates to the year, and X equals 0 is 2000, X equals 11 is 2011. So if I'm looking for 2007, I would just put in 7
Okay.
for X. I would put in 7 right here, square it times 627. Put in X here, times it by -3, and add 11,500. Boom. Okay, so in this question, I want to know the minimum and maximum. And honestly, it's almost like I could just plug in numbers. I could plug in all 11 years and find where the minimum and maximum is. I think it does. Let's see. But I guess there could be something going on with in between years. That could be a problem. Yeah, it could be in between years. So it might take me a while to really zero in on the maximum and minimum. So let's solve it with calculus. Let's do it the exact same way we solved the first problem we started with and the problem we just solved. Let's find where this function is the lowest and where this function is the highest. So let's look for local extrema, and let's decide if those local extrema are absolute extrema. All right, so what do we do? What do we do if we want to find local extrema for this or any function? Yep, we find the derivative, and the derivative is going to tell us where the inflection points are. Where the derivative equals 0 gives us the critical numbers. So let's find the derivative. Let's do it. F prime of x equals, what's 2 times 620? 7? 1254 times x minus 3530. And this goes away. Well, this looks easy, right? I spend more time talking about it than actually doing. All right, so what's our next step? We've got the derivative. Now keep in mind, this is an important point. We're going to come back to this, and we're going to plug in numbers and say, all right, at this point, is the derivative positive or negative? But what's our next step right now? Exactly. Find the critical numbers. How do we find the critical numbers, Nikita? The critical numbers are where something equals 0. Right? Where something equals 0. Where what equals 0? The critical numbers are where something equals 0. What equals 0 when the critical numbers? Derivative. Where the derivative equals 0. We have the derivative. We want to know where it equals 0. And when we find where it equals 0, those are our critical numbers. All right, so let's make this 0, and let's make this so that it equals 0. Okay, easy peasy. Let's add 3530 to both sides. We get 3530 equals 1254x. What do we do now? Divide by 1254. Divide by 1254. What do we get? 3530 divided by 1254? 2.81 equals x. Easy peasy. We don't have two critical numbers, we only have one. Rocking and roll. So, we know that when f prime is 2.81, that it is 0. We just need to know what's happening on either side of that, and that will give us all the information we need to know about local minimum, local maximum, absolute minimum, absolute maximum. So let's do our line. Let me even do it. Let's do it right here. Got a good feeling about this. I can make it fit. All right, so I'm looking at x equals 2.81. Let's choose one number to the left of that, one number to the right of that. And we know the function is only relevant between 0 and 11. So I guess just to be safe, we should choose numbers between 0 and 11. But that's fine, because we can choose 0. And we can also choose 10. That might be easy for us. So at this point, we need to know what is the slope when x equals 0. And if it's positive, we know it's increasing. If it's negative, we know it's decreasing. What is the slope when x equals 10? And if the derivative is positive, we know it's increasing. The derivative is negative, we know it's decreasing. So we put in 0 into something. What do we put 0 into? Yeah, we put 0 in here. You got it. All right, we put f prime of 0. What do you get? Negative?
3.30.
Yeah, fantastic. Negative 3,530. This is 0. So we know it's negative. The slope is negative at f equals 0. So the function itself is back here. The slope, the f prime, is 0, or negative, excuse me. So what do we know about the function itself?
Decreasing.
Fantastic. All right, let's do 10.
90.
Positive, right?
Positive.
All right. The slope is positive, so that means the function itself is
Increasing.
boom. All right. Now what do we know?
Extrema.
Local extrema. And is it an absolute extrema? Yeah. All right. So talk me through. We can just verbalize what we know at this point. We really can. What do we know?
I think like before 2000 to 12. Between 12
Yeah,
and
this is
13.
2002, like in October or something like that. Before 2002, October 5th or whatever.
The number of employees I had was decreasing. After 2002 till 2010, the number had increasing by whatever 90.
Yeah. So then what do we know about October of 2002? Was it the highest point of employee numbers or the lowest point of employees?
Lowest.
Yeah, it was the lowest point. The lowest point on this interval. Now, here's an interest. So we know this is an absolute minimum. So let's plug this back into a function and figure out how many employees we had on October 5th, 2002. So we need to plug this back into some function and find out how many employees we had on that day. All right, so which function do we put that into?
Top.
Top. Right, makes sense, Shiva?
Yes.
This tells us how many employees. This derivative just tells us the rate of change, but we want actual employees. All right, and then, so how many employees do we have at this point? Sorry, I guess you can do it. Just put 2.8 squared times 627 and figure out how to do this somehow on your calculator and add 11,500 to it.
negative 4933.
I'm not liking that. I don't know how you can have negative employees. I mean, I've had few coworkers who were pretty much worthless before, but I don't know if we can call them negative numbers. How much? 627. I'm liking the 6. 6 something. Help us out, Sanjay. You just have two calculations to do. 2.81 squared times 627. Maybe write that down on a piece of paper. Times 2.81 times 3530. Subtract it and then add 11,500 to it.
Yeah, I did that. We're all not getting anything around 6.
6,000? You getting something around
I'm
6,000?
actually getting 11,000 something.
All right, I'm liking 6,000 something. Shiva, you got that nice new calculator. I remember when you tried to do everything with your cell phone.
After you.
Let me see if I can do it. Can I do it? Can I save the day here? My own problem? Alright, so 2.81. Where's the square? No, I give up. I give up easy. Alright.
Now I'm getting 10,000.
Alright, what's 2.81 squared? Just put in 2.81 squared. Can you two do that? 2.81 squared. And times that by 627 and tell me what you get.
4950.
4950.9.
0.85.
Okay? Now take 2.8 times 3530.
9884.
9884. Okay. So take 4950.9 minus 9884 plus 11,500.
Do the rest.
Okay. All right, what do you get?
$6,566.84.
Beautiful. Okay. That 0.84, that was somebody who was in accounting who wasn't really a whole person. Okay. So 6,000. So that's the minimum number of employees over this time period. Next and last question on this. What is the maximum number of employees over this time period?
10.
Close. Now, we just chose 10 as an
11.
estimate. 11. We know that this graph goes all the way to 11. Yeah. We need to plug 11. Will that necessarily give us the answer? Look up here, Nikita. You can figure it out. What about 0? What about 2,000? Could this be higher than this? Why not?
Yes.
It could be. All we know is that it is decreasing on this interval, which means as we went back in time, it would be increasing. So we just need to plug the extremes. And we know that we only need to look at the extremes because from here to the right it gets lower and lower. So this is the highest point on this interval. And we only need to plug the extreme on this end because before that it is increasing. So everything to the left of that is lower. So we need to plug in 0 and we need to plug in 11 to which function? Yeah, the first one. Okay, so 0 should be easy. The 0 minus 0, so 11,500. Okay. And now, put an 11 to this function. Dare we try? Beautiful. 537? Okay. So what is the maximum number of employees employed at Amazon over this time period? And the minimum number employed over this time period?
6,000.
6,000 is lower than the 500. We also know that it was decreasing when they had 11,500 in 2000. Maybe this is right after the dot-com bubble burst. Might have been it. Okay. Makes sense. Should we go home? You want to do one more? I will be here if anyone wants to do more or ask more questions. But that's it. You have survived calculus. And hopefully you've gotten an idea of how to answer some useful business questions with calculus.
So for the next week, it will be the same type of homework? Please for the next week?
So the quiz for Chapter 12 will be, I think, just one of these problems. And hopefully you can get that done. And then next week we'll just review everything. We'll start at the beginning. And I'll base the review and the final exam on the quiz questions. So if you can do the questions on the quiz, you should ace the final. So that's how we'll do the review next week. We'll just start quiz number 1. All right, this question makes sense. This question makes sense. And I think that's the way to plan your studying.
How many questions you don't
Don't know. I haven't made the final yet.
have? Okay.
But I'll work out those details.
Thank you.
You bet. Have a good night.